Welcome to Advanced Module 03 on air-cooled chiller systems. Today, we'll explore how to design and operate an air-cooled chiller plant specifically for tropical ambient conditions, while ensuring resilience during partial loads and equipment failures. We'll cover key components including the condenser fans, chilled water pumps, chilled water headers, buffer volume, and chiller plant operator sequencing. This training will deepen your understanding of these critical elements to optimize performance and reliability in demanding environments. This module focuses on air-cooled chiller systems, specifically designed for tropical climates with an emphasis on high efficiency and rapid thermal recovery. Our purpose is to convert protected load, climate, and availability goals into a clear, auditable air-cooled plant design, while respecting OEM limits and local safety standards. By the end of this training, you'll be able to calculate site duty, flow, derating, thermal storage equivalent, and buffer volume. You'll also learn how to define restart milestones and validate maintenance and failure states. This module targets owners, operators, engineers across mechanical, electrical, and controls disciplines, commissioning authorities, and vendor or service teams. Key components include air-cooled chillers, condenser fans, chilled water pumps and headers, as well as buffers and chiller plant optimizing systems. We'll also address sustainability through LEED scores and low GWP refrigerants, resilience via uptime targets and timed recovery, and support everything with certified performance and field-proven data. This comprehensive approach ensures reliable, efficient operation tailored to real-world demands and standards. In this module, we focus on air-cooled chiller systems within the Data Center MVAC context, evaluated through a risk lens and decision hierarchy. We look at safety, thermal continuity, maintainability, efficiency, and evidence all together to make informed decisions. Starting with safety, it's crucial to prove evaporator flow before enabling the compressor, adhere strictly to pressure, anti-cycle, electrical, and ambient limits, and never bypass local safeties. For continuity and maintainability, we emphasize a distributed modular duty approach, ensuring independent power and controls, allowing isolation of one module without losing required service, and always proving return-to-service capability. Lastly, performance and evidence involve selecting equipment based on actual site ambient conditions, meeting project sustainability goals like LEED or Green Mark, and recording key parameters such as load, power, flow, temperature, and recovery on one synchronized clock for accuracy. Just a quick note, CHW stands for chilled water, COP is coefficient of performance, TSE is total cooling system efficiency, and TES means thermal energy storage. In this module, we focus on air-cooled chiller systems within Data Center MVAC setups. The core concept here is the repeatable engineering chain that links design intent all the way to field acceptance. This chain starts with defining the intent and gathering inputs, then moves through careful calculation, selection, and architectural sequencing. We continue with metering and modeling, followed by factory acceptance testing, installation, and startup procedures. The process doesn't end there. It includes ongoing functions like failure management, recovery, restoration, trending, optimization, and finally handover. We break this into three main phases: design and calculate, control and test, and operate and improve. Each phase has critical focus areas, like ensuring protected load, high ambient capacity, and redundancy in design, establishing permissives and authorities, executing FAT and failure tests during control, and applying calibrated evidence, defect closure, and controlled optimization during operation. Understanding these steps and their integration is key to delivering reliable and efficient air-cooled chiller systems for critical data center environments. In Module 03, we focus on air-cooled chiller systems, a critical component in Data Center MVAC setups. By the end of this module, you will be able to specify, calculate, test, and operate a resilient air-cooled chiller plant with confidence. We break down learning into four key competences. First, design competence, where you'll learn to define load, climate, and system boundaries, choose the right topology and redundancy, and align rating targets with project criteria. Next is calculation competence. Here, you'll accurately calculate site duty, flow, annual energy use, total system efficiency, N+1 margin, and thermal buffer, while clearly stating assumptions and acknowledging uncertainties. Control competence covers essential operational sequences, including starting the system normally, recovering after power loss, measuring actual cooling duty, and restoring verified readiness. Finally, evidence competence ensures you can demonstrate and validate all system parameters and performance metrics. Understanding terms like chilled water, coefficient of performance, variable speed drives, and chiller plant optimizing systems will support your mastery of this module. This module focuses on air-cooled chiller systems, providing a detailed agenda that guides us through a practical workstream starting from the design basis all the way to integrated recovery evidence. We'll begin by defining the system and its boundaries, covering the key equipment and heat paths, along with the critical interfaces involving air, water, refrigerant, electrical, and controls. We'll also examine the system's performance in normal operation, maintenance scenarios, and potential failure states. Next, we'll dive into sustainability and calculation aspects, including LEED design models, Green Mark Gold Plus and Platinum certifications, and considerations for high-ambient derating. Important metrics like TSE, PUE, WUE, and refrigerant impacts will also be discussed. Then we'll explore rapid response capabilities, highlighting uptime and TIA outcomes, OEM restart benchmarks, dependencies on power and flow, thermal energy storage, and timed blackout tests. Finally, we'll cover commissioning and operations, focusing on proof levels from L1 to L5, acceptance criteria, standard and emergency operating procedures, maintenance practices, laboratory testing, handover processes, and competency requirements. It's important to note some key abbreviations we'll use throughout. CHW stands for chilled water, COP for coefficient of performance, VSD for variable speed drive, and CPOS for chiller plant optimizing system. Here we have an overview of an air-cooled chiller plant for a data center MVAC system, highlighting the key components and their functions. First, the heat rejection stage uses V-bank coils paired with axial fans to expel heat through open vertical discharge. Then, the chilled water generation relies on the evaporator and compressors, equipped with local safety features for reliable operation. The hydronic control involves variable speed drive pumps and flow meters, ensuring minimum flow is maintained and buffer volume is managed. For distribution, chilled water supply and return headers are monitored with remote differential pressure sensors to maintain balance. Finally, the data hall duty is handled by PICV-controlled CRAHs, which protect the rack inlet temperature conditions. At the core, chilled water supply flows cold to the data halls, while warm return water cycles back. This loop is essential for efficient cooling. Understanding these 5 key stages is critical to optimizing system performance and reliability. Now, let's focus on the system boundary and interface ownership in air-cooled chiller systems. Every interface within the system must have a clearly defined owner, a signal to communicate status, acceptance criteria to measure performance, and a restoration rule to guide recovery if issues arise. This ensures smooth operation and accountability across all components. Keep in mind these key terms. CHW stands for chilled water, COP is the coefficient of performance, VSD means variable speed drive, and CPOS refers to the chiller plant optimizing system. Understanding these will help us better manage system interactions and efficiency. On this slide, we focus on air-cooled chiller systems within data center MVAC setups. The key objective here is to identify the field assets, understand service clearances, and recognize failure domains specific to these systems. We'll cover equipment identification, including air-cooled chillers themselves, condenser fan arrays, chilled water pumps and headers, buffer and thermal energy storage volumes, and the chiller plant optimizing system sequencing. When inspecting these systems, it's essential to review nameplate duty and approved submittals, consider access points, isolation procedures, drainage, and lifting requirements, and check sensors, actuators, and local safety devices. Operationally, we pay attention to the lead and lag states, adjust set points and modes appropriately, and monitor flow, temperature, pressure, and power to ensure optimal performance. Understanding these elements is crucial for effective management and maintenance of air-cooled chiller systems in data centers. In Module 03, we dive into air-cooled chiller systems and their application within data center MVAC setups. A critical first step is to freeze the boundary conditions before selecting equipment or committing to a recovery time. This means clearly defining the design criteria and controlled input parameters. We need to understand the load and duty aspects, which include the protected IT and support loads, allowances for diversity and future growth, fouling margins, and scenarios for maintenance and potential failures. Climate and environmental factors are equally vital. This encompasses the coincident outdoor dry bulb temperature, solar and air recirculation impacts, altitude, and limitations related to corrosion, noise, and plume dispersion. Temperature architecture plays a defining role, covering chilled water supply and return temperatures, rack inlet temperature envelopes, permissible rates of temperature rise, as well as the minimum stable load and anti-cycle volume considerations. Hydraulic and airflow limits must also be set to ensure system stability. We also evaluate redundancy outcomes, growth and phasing strategies, electrical recovery capabilities, and the level of control authority within the system. Finally, acceptance evidence ensures the system meets all these criteria. Remember, key terms like CHW for chilled water, COP as the coefficient of performance, VSD representing variable speed drives, and CPOS for chiller plant optimizing system will frequently come up throughout this module. In this module, we're focusing on air-cooled chiller systems within Data Center MVAC setups. We'll explore the equipment and process architecture, following key paths such as energy, fluid, air, command, and evidence from their source all the way to rejection. Crucial components include air-cooled chillers, condenser fan arrays, chilled water pumps and headers, buffer volume, and CPOS sequencing. Understanding the energy path involves how these components interact to deliver and manage cooling efficiently. The control path focuses on primary duty, standby, and isolation paths, with maintenance bypasses applied only when approved. Also, the evidence path ensures operational integrity by proving evaporator flow, starting the lead chiller, enabling condenser fans, trimming chilled water leaving set points, and staging on load and runtime. This comprehensive approach helps optimize performance and reliability in air-cooled chiller systems. This module focuses on air-cooled chiller systems, specifically for data center MVAC applications. One key point is to separate capacity margin from redundancy and ensure verification at every load point and recovery state. When sizing, we start with essential inputs like the load profile, site ambient conditions, chilled water temperatures, high-ambient OEM capacity and power data, minimum flow or volume requirements, and utility transfer capabilities. We then consider boundary conditions such as normal operation, loads ranging from 25 to 100%, design day scenarios, concurrent maintenance, single failure events, and complete utility interruptions. Selection checks involve careful field verification using OEM-certified performance maps alongside measured load and weather data. It's critical to verify N+1 residual capacity to maintain reliability. Additionally, timed recovery and thermal hold strategies help ensure stability during transitions. Throughout this process, we keep in mind key terms like CHW for chilled water, COP which stands for coefficient of performance, VSD meaning variable speed drive, and CPOS, the chiller plant optimizing system. All of these help us design a robust, efficient, and reliable air-cooled chiller system for data centers. This module covers the key engineering formulas for air-cooled chiller systems, using SI units and focusing on a single declared boundary for accuracy. First, we have the evaporator duty, which is calculated by multiplying the water flow rate, specific heat, and temperature difference. This requires simultaneous flow and chilled water supply and return temperatures. Next, water flow is derived by dividing the evaporator duty by the product of specific heat and temperature difference. For water at room temperature, kilograms per second roughly equals liters per second, simplifying conversions. Heat rejection equals the sum of evaporator duty plus the compressor power input, reflecting the total load that condenser coils and fans must dissipate. The chiller's coefficient of performance, or COP, is the ratio of evaporator duty to chiller power input, ensuring comparisons are consistent by maintaining the same ambient and water conditions. The green mark TSE metric sums all prescribed ACMV power over cooling capacity, considering both water and air side equipment within the defined boundary. For site duty modules, calculate the number of modules needed by dividing the design load by the module capacity, adjusting for ambient and installation factors. The thermal buffer volume is based on the heat duty, time, fluid properties, and temperature differential, with allowances for unusable volume and system uncertainties. Finally, recovered duty is calculated from synchronized operational data to provide an accurate measure of system performance, rather than relying on nominal capacity alone. Each of these formulas is essential for precise design and evaluation of air-cooled chiller systems. In this module, we're focusing on air-cooled chiller systems within Data Center MVAC setups. A key point to understand is the certification logic, which compares rating outcomes against actual chiller requirements. It's important to note that achieving gold or platinum certification is not just about hitting a single chiller COP. Instead, we translate the selected rating route into measurable project design criteria and evidence requirements. For LEED certifications, gold requires 60 to 79 points, while platinum needs 80 or more. The Data Center Energy Credit uses approved whole building or system modeling, along with contributions from commissioning, refrigerant management, and water strategies. Meanwhile, the BCA-IMDA Green Mark DC 2024 standards set Gold Plus at 40 points or higher and Platinum at 50 or above, with mandatory thresholds for power usage effectiveness, total cooling system efficiency, and requirements for permanent measurement, verification, water usage effectiveness, and resilience. When dealing with air-cooled projects, there's no cooling tower coefficient of cooling calculation, since these chillers operate dry. The focus instead is on annual energy use, capacity under high ambient temperatures, total cooling system efficiency, PUE, refrigerant global warming potential, water usage boundary, and rapid recovery performance. Remember, terms like CHW stand for chilled water, COP is coefficient of performance, and TSE means total cooling system efficiency. This slide focuses on translating LEED and Green Mark certification requirements into actionable air-cooled plant design strategies for data center MVAC systems. The framework here breaks down public certification criteria into specific project design responses and associated field or model evidence. For LEED certification, achieving gold or platinum status depends on coordinating and optimizing the entire project scorecard, including energy performance models that integrate IT, power, and HVAC interactions. Water management is also crucial. Dry air cooling helps avoid routine tower makeup, and site water balance must consider all pathways like humidification. Refrigerant impact is addressed by selecting low GWP options and maintaining thorough commissioning records. On the Green Mark side, ratings focus on modeling various IT loads and strict efficiency targets, with continuous measurement and verification ensuring the system performs within defined benchmarks. The last section emphasizes a clear process. Define the criteria, model the system, meter performance, and certify compliance. This structured approach ensures design aligns with sustainability goals and certification standards. Here we have a worked example demonstrating a LEED cooling energy design check for an air-cooled chiller system. The annual cooling load is 12,500 megawatt-hours thermal, which is the amount of cooling delivered by the system. This example helps support design decisions, but does not alone determine LEED points. Looking at the baseline input, the system requires 3,150 megawatt-hours of energy annually. With the proposed system improvements, that energy drops to 2,350 megawatt-hours, resulting in an energy reduction of 800 megawatt-hours per year, or a 25% savings. The coefficient of performance, or COP, reflects this efficiency change. The baseline COP is 3.97, calculated by dividing the cooling output by the baseline energy input. Meanwhile, the proposed COP improves to 5.32, showing a more efficient system. It's important to note that this example focuses only on the cooling subsystem. The whole model includes IT load, electrical systems, HVAC, and other factors, and to properly pursue LEED certification, the approved LEED path and comprehensive project model must be used. This example is strictly for training and illustration purposes. Here we have a worked example that covers key concepts like high ambient capacity, design margin, and N+1 redundancy for air-cooled chiller systems in a data center environment. The protected load is 2.2 megawatts, and with a 10% design margin, this brings our total design duty to 2,420 kilowatts. Given the site ambient temperature of 40 degrees Celsius dry bulb and an 8 Kelvin chilled water temperature difference, each module's net capacity at site conditions is 450 kilowatts. To meet the design duty, We calculate the number of duty modules by dividing 2,420 by 450, which rounds up to 6 modules. For an N+1 configuration, we add 1 standby module, resulting in 7 total modules installed on site. This gives us a residual duty capacity of 6 times 450 kilowatts, or 2,700 kilowatts, which provides a residual margin of 280 kilowatts, or 11.6%. This margin helps ensure reliability under varying conditions. Finally, the design chilled water flow is determined by dividing the design duty by the product of water's specific heat and the temperature difference, resulting in about 72.3 liters per second. It's important to note that these figures are illustrative. Final module selection must always be based on certified OEM data that accounts for actual site conditions, including variables like coil inlet recirculation, altitude, fouling, sound, and electrical capacity. Here we focus on air-cooled chiller systems within Data Center MVAC setups, particularly under the BCA-IMDA Green Mark DC 2024 benchmarks. It's important to understand that the air-cooled topology must meet overall cooling system efficiency standards and measurement boundaries. The performance certification is divided into Gold Plus and Platinum levels, with scores starting at 40 points for Gold Plus and 50 points for Platinum. Key metrics include power usage effectiveness, or PUE, which should be no higher than 1.46 for Gold Plus and 1.39 for Platinum at 25% IT load. Total cooling efficiency targets are set at 0.74 kilowatts per refrigeration ton for Gold Plus and 0.68 for Platinum, and these efficiencies must be maintained across IT loads from 25 to 100%. The design also requires permanent monitoring and verification with highly accurate data logging, keeping result variances within 5%. Additionally, the water usage effectiveness, or WUE, plays a role, awarding points based on annual site water use relative to IT energy consumption. This comprehensive approach ensures that air-cooled chiller systems are rigorously evaluated for energy and water efficiency throughout their operating range. Here we have a worked example focusing on a Green Mark Platinum total cooling power budget for an air-cooled chiller system in a data center. The cooling duty is set at 625.5 refrigeration tons, or RT. The Platinum limit for this example is 0.68 kilowatts per RT, which means the maximum allowed total air conditioning and mechanical ventilation, or ACMV, power is 425.3 kilowatts. Breaking down the actual power consumption, the chiller and fans operate at 370 kilowatts, 2 chilled water pumps at 18 kilowatts. Data hall fans contribute 25 kilowatts, and other ACMV components like humidity controls, office systems, and controls use 5 kilowatts. This brings the total example power consumption to 418 kilowatts, which is just under the prescribed cap. The key performance metric, the total system efficiency, or TSE, calculated as total power divided by cooling duty, comes to 0.668 kilowatts per RT, comfortably within the Platinum standard of 0.68. The strict criteria include worst-case TSE values at various design loads, continuous compliance through full operation, 1-minute measurement and verification, and optimized design parameters like high chilled water temperatures and low-pressure drop airflow. If the selected equipment and design exceed the 425.3 kilowatt limit at any load point, the system fails the Platinum TSE requirement, which means adjustments are needed in temperature settings, equipment choices, airflow patterns, hydronics, or system topology to meet this high-efficiency standard. Here we see the engineering decision path for air-cooled chiller systems, which follows a rigorous process: calculate, challenge, and accept. A number becomes a design commitment only after it passes certified selection, failure state checks, and field evidence validation. We start with a controlled input basis, then perform checked calculations to interpret the engineering meaning behind the numbers. Margin is assessed by considering capacity and potential failures. Verification involves both the OEM's data and site proof, ensuring the design is robust under real conditions. Acceptance happens only with authorized evidence backing it up. The process emphasizes verifying every declared state and reviewing redundancy across distributed modules, power, controls, sensors, and service access. The evidence package includes calculations, certified performance maps, method statements, raw synchronized data, defect tracking, and signed restoration documents. The decision rule here is clear. Accept only when capacity, efficiency, and recovery are all proven at the declared operating state. This thorough protocol ensures reliability and optimal performance in chilled water systems. Here, we're focusing on the control sequence for air-cooled chiller systems used in data center MVAC setups. The sequence involves several critical steps, starting with proving evaporator flow, which ensures the system is ready for operation. Next, we enable the condenser fans, a key process that allows heat dissipation. Then, we proceed to start the lead chiller, which serves as the primary cooling unit. These steps are carefully staged to optimize system performance and reliability. Throughout this process, monitoring and controls like COP and VSD play important roles to maintain efficiency. Understanding this start, stage, fail, and restore sequence is essential for managing advanced chiller operations effectively. In this module, we're focusing on air-cooled chiller systems within data center MVAC setups. Specifically, we'll explore the uptime tier and ANSI/TIA 942 standards related to cooling performance. These public frameworks define the system's topology and resilient outcomes, but it's crucial that each project clearly declares and tests its actual seconds to capacity requirements. Starting with Tier 3, which is rated 3, the key feature is concurrent maintainability. This means the system has redundant capacity components and distribution paths, allowing any planned maintenance to be performed without losing the necessary cooling service. Moving up to Tier 4, or rated 4, the system must be fault-tolerant, providing protection against a single failure. It should maintain stable cooling even through mechanical restarts after a utility interruption, and importantly, no common control or path should compromise this outcome. Owners must specify performance requirements carefully, since there's no universal public full-load restart number. They need to define critical parameters like detection, usable power, chilled water path, compressor start sequences, operation at 80% duty, full required duty, thermal envelope, and restoration processes. Finally, keep in mind the key abbreviations. CHW stands for chilled water, COP is the coefficient of performance, TSE means total cooling system efficiency, and TS refers to thermal energy storage. These terms are essential for understanding and evaluating system performance. On this slide, we focus on rapid recovery terminology to help us avoid ambiguous vendor promises when dealing with air-cooled chiller systems. It's crucial that we use the same defined milestones throughout the entire process, from the owner's project requirements and basis of design, through procurement schedules, sequences, factory acceptance testing, site acceptance testing, and integrated systems tests. We start by defining each key term with its precise meaning, clarifying what it does not prove, and specifying the acceptance signal we should look for. For example, when we say control power restored, it means the controller is energized and stable, but it does not prove compressor or cooling capacity. The acceptance signal in this case is voltage presence, controller ready status, and a timestamp. Similarly, chiller ready indicates that permissives are true and the start has been accepted, but again, it does not confirm the compressor is running until we observe the motor or variable speed drive operating. Moving on, cooling available means chilled water flow and a useful temperature difference have been established, but to confirm 80% or full capacity, we look for measurements like mass flow rate times specific heat capacity times temperature difference, all synchronized on a common clock. Ultimately, full required duty means the plant duty is approved and stable, with normal readiness restored and capacity hold plus alarms and standby systems normal. This structured approach ensures clarity and consistency, minimizing misunderstandings and improving communication across all project stages. Defining and instrumenting these terms precisely is key to achieving reliable and measurable system performance during recovery. This slide covers critical timing milestones for air-cooled thermal recovery in data center MVAC systems. The key point here is that these recommended criteria are designed for procurement and testing, not absolute mandates, and adjustments should only be made following approved transient analysis. Starting with outage detection, the system should interrupt the normal power source within 0 to 2 seconds, capturing the cause and event timestamp. Then, a usable alternate power source should be established in roughly 10 to 15 seconds by recording the generator or transfer sequence and monitoring voltage and control power. Next, the chilled water path must be verified within 25 seconds through automatic pump and valve sequencing, ensuring independent flow proof and a sufficient minimum flow margin. The first compressor should be running in under 60 seconds, operating in the OEM's rapid restart mode while maintaining necessary safety checks and at least 80% duty. Within 150 seconds, the system calculates simultaneous waterside cooling demand by analyzing flow and temperature trends. Finally, full plant capacity recovery targets a maximum of 180 seconds, though never exceeding the approved bridging time, holding until stable control and normal operation is confirmed. These milestones, trip, transfer, recover, and restore, outline a tight, systematic response to maintain critical cooling with high reliability. On this slide, we focus on public air-cooled rapid restart benchmarks, which serve as an important procurement reference for data center MVAC systems. These claims are specific to the original equipment manufacturer's models and options, so it's crucial to obtain certified project curves, understand dependencies, and witness complete system tests before making decisions. For example, the Dakin Pathfinder and Trailblazer systems can start as fast as 35 seconds, but this depends on factors like the rapid restore option, controller state, power, and ambient conditions. Dakin's fast loading feature can reach full load in under 5 minutes, keeping in mind the applicable model configurations and loading limits. Train's RTF and ACR models reboot in about 45 seconds, with performance influenced by prior system state, controller, and restart settings. Their system can reach 80% load in less than 2.5 minutes, again depending on model specifics, flow, ambient, and load conditions. York's YVA model can restart compressors as quickly as 34 seconds when equipped with an optional feature, considering the variable speed drive and power quality. The York IVAM achieves full load in as little as 3 minutes, influenced by model choice, emergency power management, and site selection. In summary, it's vital to compare these benchmarks, specify appropriate models, witness tests, and accept performance based on solid, witnessed data to ensure optimal system operation. Here, we're working through a detailed example of sizing a thermal buffer for air-cooled chiller recovery in a data center MVAC system. The protected cooling load is 20 megawatts with a usable water temperature rise of 4 Kelvin. We have a full-duty recovery target of 180 seconds plus an additional 60 seconds engineering margin, totaling 240 seconds. Starting with that, we calculate the energy bridge as the product of the load and the total time, arriving at 528,000 kilojoules. Next, we determine the capacity per cubic meter, based on the density and specific heat of water multiplied by the 4 Kelvin temperature rise, giving us 16,710 kilojoules per cubic meter. Dividing the energy bridge by this capacity yields the theoretical volume of 31.6 cubic meters. Applying a design factor of 1.20 for safety and operational considerations, we get a final design volume of approximately 38 cubic meters. We also include a 300-second case from the original equipment manufacturer, which suggests a buffer volume closer to 57 cubic meters for extended recovery. Finally, dynamic verification is essential. This involves analyzing factors like mixing, usable volume, pump transition behaviors, bypass valves, sensor delays, and load profiles. The buffer must support the entire measured system recovery time, validated through transient simulations and actual load outage tests, not just the controller reboot period. This approach ensures reliable system recovery and protection. In this slide, we're looking at the concept of rapid restart evidence architecture for air-cooled chiller systems in data center MVAC applications. The key idea here is that we capture electrical, mechanical, controls, and thermal responses all on one synchronized clock, because just knowing status alone doesn't prove that the system has fully recovered its duty. Starting with electrical signals, we track elements such as the normal power source, generator or automatic transfer switch, usable bus voltage, breaker or variable speed drive status, and step load events. For mechanical aspects, we confirm valve and pump proof, chilled water flow, compressor and fan states, along with buffer discharge. Controls data involves detection, permissives, commands, proof signals, alarms, fallback conditions, and restoration. Thermally, we monitor chilled water supply and return temperatures, calculate duty, check rack inlet temperatures, rate of temperature rise, and stable hold conditions. By aligning these signals precisely in time, we can establish critical milestones like usable power availability, complete water path conformation, compressor running versus loading states, and actual recovered cooling duty, all within 1 second or faster. Finally, the rack inlet temperature verifies a protected environment to ensure thermal continuity is maintained. This integrated approach is essential to accurately verify that the air-cooled chiller system has fully restarted and resumed its designed cooling performance. This slide focuses on the integrated recovery acceptance process for air-cooled chiller systems in data center MVAC setups. The key goal here is ensuring that when power is lost and then restored, the system returns to full readiness seamlessly. We execute tests at representative loads using calibrated instruments, with explicit abort limits and authorized witnesses in place, following a one-step restoration plan. The acceptance criteria involve alternate power sources that must be ready and usable by approved milestones, along with removing the normal power source to simulate outages. During testing, we monitor the chilled water path to ensure flow never drops below the OEM minimum, using automatic standby pumps and valves, while tracking command signals, proof, flow, and differential pressure. Chiller restart is critical. The first compressor must come online within an approved time frame, restarting under representative load conditions, while carefully monitoring controller parameters, speed, current, pressure, and alarms. Recovered duty targets require achieving 80% and full load by specific approved times, calculated via synchronized flow, temperature differential, and power consumption of chillers, fans, and pumps. Thermal continuity must be maintained inside the chilled water supply and rack inlet envelope throughout recovery, keeping temperature rise and maximum temperature within limits. Finally, restoration returns the system to normal lineup with alarms cleared and standby equipment ready, followed by controlled return and retesting. Documentation like signed restoration sheets and indexed raw data provide the required evidence to confirm successful readiness. This thorough process ensures reliability and safety for critical cooling in data centers. This module focuses on air-cooled chiller systems within data center MVAC setups. One key point is that procurement must verify the entire chain from emergency power all the way to stable cooling performance, considering the project's ambient conditions and load. Starting with the electrical and controls aspect, it's crucial to have uninterrupted power supply or ride-through capabilities for controllers and networks, manage generator step-load impacts and harmonics, understand variable speed drive inrush behavior, set appropriate breaker and load shed priorities, and maintain accurate timing with retained clocks. On the OEM refrigerant machine side, attention is needed on controller reboot processes, minimum off time and pressure equalization to protect components, initial compressor run time, following the loading curve up to 80% and full duty, and adapting to actual ambient and chilled water conditions. For the hydraulic and thermal system, proof of pump and valve flow, maintaining minimum flow and volume, buffer or thermal energy storage integration, common header isolation, monitoring rack inlet rate of rise, and managing both normal and standby restoration processes are essential to reliable operation. Remember, chilled water is abbreviated as CHW. COP stands for Coefficient of Performance. TSE is Total Cooling System Efficiency, and TES means Thermal Energy Storage. Understanding these factors ensures a robust and responsive air-cooled chiller system for critical data center environments. This slide focuses on the chiller capability schedule and the hierarchy of authority and acceptance ownership in air-cooled chiller systems for data center MVAC. Every requirement is linked to its true owner. So what's preferred by one project isn't mistakenly applied as a universal standard. We have three main categories. First, the standards and certifications, things like uptime tier 3 or 4, TIA rated 3 or -4. These define maintainability and fault tolerance, while organizations like ASHRAE, AHRI, LEED, and Greenmark focus on safety, performance, and rating results. Next, the owner's project requirements detail specifics such as seconds to capacity, chiller-only power usage in kW per ton, equipment harmonic distortion current, charge ratios, and valve timing. These become mandatory when specified in the owner's project requirements, basis of design, and contract documents. Finally, the OEM, authority having jurisdiction, and site qualifications cover certified operating maps, restart curves, local safety limits, refrigerant classifications, compatibility with generators, plus environmental qualifications like seismic, wind, and corrosion resistance, often verified through witnessed proof. This clear assignment of responsibilities ensures everyone involved understands their role, which greatly supports project success and operational reliability. This slide focuses on air-cooled chiller systems within Data Center MVAC setups, highlighting their capability schedule in terms of response, power, and efficiency. The values presented here are mandatory only when incorporated into the owner's project requirements or basis of design, with standards and certified data serving as the governing acceptance basis. Key capabilities include rapid source loss recovery, where detection occurs within 2 seconds and compressors respond fully within 3 minutes. Power inputs must feature independent A and B paths with controls designed to either ride through disturbances or recover predictably, supported by approved OEM designs and thorough failure mode testing. Power quality is critical, with total harmonic distortion limited to less than 5%, meeting IEEE standards at the point of common coupling. Part load chiller input is expected to be below 0.65 kilowatts per ton under specified conditions, verified through AHRI certification and performance checks across multiple load points. The whole cooling system must achieve target metrics like a GM technical score efficiency of 0.74 or better, aligning with LEED Gold or Platinum standards where applicable. Although cooling tower certification isn't applicable for dry condensers, water usage efficiency and system boundaries must be carefully recorded where water is used. Finally, the process is summarized in 4 key steps: classify, specify, measure, and accept, ensuring a structured approach to managing system performance and compliance. This slide focuses on the air-cooled chiller capability schedule, specifically highlighting refrigerant selection, hydraulic isolation, site qualification, and serviceability requirements. The key takeaway here is that environmental and physical targets demand model-specific documentation and compliance with local jurisdictional regulations. Starting with refrigerant selection, the goal is to choose a refrigerant with the lowest practical global warming potential, ideally below 700, while ensuring safety and availability. This selection must comply with standards like ASHRAE 34, ASHRAE 15, local authority having jurisdiction requirements, and LEED or green measures. Acceptance proof involves reviewing refrigerant type, charge quantity, safety considerations, and environmental impact calculations. Regarding refrigerant charge ratio, it should typically be under 2.5 pounds per ton to meet owner requirements, help preserve certified performance and serviceability. Because there is no universal standard, metrics are based on manufacturer specifications, divided by capacity ratings. Hydraulic isolation involves installing motorized boundaries, but only allowing isolation for less than 30 seconds after transient system reviews. This ensures maintainability goals align with the owner's operation sequences, proven through valve timing, transient records, and isolation tests. Site qualification covers ambient conditions, including solar heat, air recirculation, altitude, and corrosion risks. Equipment must meet AHRI and OEM limits while matching project environmental factors. Wind and seismic requirements are dictated by site codes, applying high wind ratings only where hazard analysis justifies them. Certification of anchorage and thorough inspection upon installation are critical. Finally, replacement and serviceability demand that individual modules or fans can be removed without compromising required service, supporting Tier 3/4 or rated 3/4 objectives. Maintenance tests must be recorded along with access and restoration procedures. Throughout, the process follows 4 key phases: screen, qualify, install, and prove, to ensure full compliance and operational reliability for air-cooled chiller systems in data center MVAC applications. In this module, we focus on air-cooled chiller systems within data center MVAC setups. A key takeaway is the importance of a resilient power and controls architecture to ensure the entire cooling chain remains reliable and efficient. For optimal fault tolerance, dual terminals or internal transfer devices must maintain a manageable end-to-end topology at the chosen rating. To achieve robust operation, independent delivery paths are critical. This means tracing A to B power sources through every component: switchboards, breakers, cables, control power, networks, chilled water pumps, and each chiller or fan train. while eliminating shared transformers, PLCs, selectors, and communication gateways to avoid single points of failure. Transfer and ride-through capabilities are equally vital. Controllers, networks, and critical actuators should remain operational or restart predictably during power events. This involves verifying generator voltage and frequency, staging motor enablement, retaining anti-cycle and pressure safeties, and using internal automatic transfer switches only when supported by listing, failure mode, effect analysis, and maintenance access. Finally, acceptance proof involves comprehensive testing and documentation, including single-line and controls failure mode and effect analyses, selective coordination, source and path isolation, black start and transfer tests, and verification of alarm and timestamp integrity. Measuring flow multiplied by delta T gives true duty confirmation. Simply showing a green run status is not sufficient proof of capacity. Now let's dive into the coordinated acceptance method for generator, VSD, and harmonic qualification. The primary goal here is to maintain equipment current distortion, or THD, below 5% at a specified point of common coupling, or PCC, which aligns with IEEE 519 standards. First, we define the PCC by establishing utility and generator boundaries and identifying key parameters like state voltage, source impedance, and measurement location. Next, we build a comprehensive load model that includes the chiller and all auxiliaries such as compressors, condenser fans, and chilled water pumps. Then we set the equipment target by specifying a THD of less than 5%, naming terminals, load ranges, and filter configurations. For system acceptance, we apply IEEE 519 to check voltage and current distortion against the project study. We also verify the generator response for kilowatt and kilovolt ampere capacity, transient steps, and ensure proper voltage and frequency recovery during dips. Protection strategies include coordinating VSD trips, breakers, relays, and fault detection logic for ride-through and selectivity. Factory-proof tests cover source and control scenarios like transfer and restart inhibition, while site-proof involves generator mode integrated system testing with trending of total harmonic distortion, voltage, frequency, and other critical parameters to ensure reliable operation. This slide covers the critical aspects of air-cooled chiller system certification and performance acceptance in data center MVAC systems. The foundation here is using AHRI-certified data at the exact project operating points to ensure accuracy. Even in modular arrays, a comprehensive system controls and performance test is essential. We start with a full-load site point, focusing on the net required duty and efficiency under design outdoor temperature and chilled water conditions. This requires AHRI 550/590 or 551/591 certified ratings, verified through OEM selection outputs. For part load performance, stable and efficient operation across 25% to 100% rated load is key, supported by AHRI's certified efficiency and pressure drop maps, plus project load profile overlays. At high ambient conditions, the goal is to avoid hidden capacity loss, pressure trips, or fan limits at site extremes, validated through certified maps and OEM application data, along with witnessed high ambient simulations or tests. The green mark budget ensures all ACMV power maintains worst-case thermal stress within rating thresholds, backed by specific standards like the BCA-IMDA 2024. Energy modeling supports whole project improvements for certifications such as LEED, using approved baselines and commissioning evidence. The final stage is field reconciliation, where measured load, power, and conditions must align with approved tolerances, relying on detailed operational plans and calibrated measurements. The process culminates in steps to select, certify, commission, and trend system performance for ongoing success. This slide covers key design requirements for air-cooled chiller systems, focusing on safety, environmental impact, and resilience. Starting with safety classification, it's crucial to use current toxicity and flammability classes alongside concentration limits, following ASHRA 34/2024 and the authority having jurisdiction. System safety involves applying safeguards like access controls, ventilation, detection, and emergency provisions, all guided by ASHRA 15/2024 and local codes. Environmental impact is addressed by calculating lead and greenhouse gas impacts, controlling leaks, and planning for refrigerant recovery at end of life. When tracking refrigerant charge intensity, owners should monitor pounds per ton or kilograms per kilowatt as a metric, without implying a fixed limit. Isolation pertains to maintaining safe chilled water and electrical boundaries while respecting transient limits, verified through documentation, lockouts, and testing. Finally, outdoor hazards such as wind, seismic activity, flooding, debris, corrosion, sound, and access must be qualified with input from jurisdiction authorities, insurers, and owners to develop a comprehensive structural and environmental qualification package. These steps align under the framework of classify, engineer, test, and control to ensure certified performance and maintainability while minimizing environmental impact. This slide outlines a comprehensive schedule for procurement, factory acceptance testing, site acceptance testing, and integrated capability acceptance for air-cooled chiller systems in data center MVAC applications. It highlights that no capability can be accepted based solely on brochure claims. Every promise must be backed by a clear condition, method, timeline, required witness, tolerance, and restoration plan. The process begins with specifying requirements and verifying selections through detailed reviews and certifications, including OEM selection, efficiency ratings, and electrical compatibility. Factory acceptance testing involves rigorous, witness tests under simulated conditions to ensure functionality, safety, and repeatable restarts. Finally, site acceptance confirms flow, isolation, communication, and metering calibration through functional tests, with performance verified against integrated utility loss and thermal envelope criteria. Throughout, requirement traceability is maintained with signed matrices and authority approvals to ensure full accountability and readiness restoration. This structured approach guarantees that the system meets all operational expectations before final acceptance. On this slide, we're focusing on tropical high-ambient operation for air-cooled chiller systems, especially looking at airflow, derating, and recovery. A key issue to watch out for is poor installation, where hot discharge air can recirculate back into the coil intake. This recirculation causes the coil inlet temperature to rise, which in turn increases the condensing temperature. As a result, system capacity decreases while input power goes up, leading to inefficiency. To address this, engineered airflow is critical. This means having an open discharge, separated air intakes, and appropriate service access to maintain proper cooling. When conditions worsen, the chiller may need to stage or derate to protect itself, and then recover. The essential selection rule here is to always prove capacity and power at the project's design ambient, including any recirculation risk, and make sure to preserve OEM clearances, maintain vertical discharge, and keep the coil clean for optimal performance. This slide explains the working principle of the air-cooled chiller system, which is crucial for cooling data centers efficiently. Starting in the data hall, the server heat warms the return air, and this heat is transferred to the chilled water through the CRH coil. This chilled water loop then pumps warm water through the chiller evaporator at a carefully controlled flow rate. Inside the refrigerant circuit, evaporation absorbs the heat, and the compressor raises the pressure and temperature of the refrigerant. Finally, the condenser coil and axial fans reject this absorbed heat, along with the compressor heat, directly to the outdoor air. What's important here is that this system uses a single water circuit and a sealed refrigerant circuit, eliminating the need for a condenser water loop or cooling tower. Control proof is maintained by ensuring the chilled water flow is verified before enabling the compressor. The system then controls the leaving water temperature, fan speed, and refrigerant pressure, while keeping alarms, staging, and standby recovery functions aligned over time. This method ensures reliable, efficient cooling tailored for data center demands. This slide covers the critical elements for monitoring and controlling air-cooled chiller systems in a data center MVAC setup. We use advanced instrumentation and a green mark measurement and verification approach to ensure efficiency and provide clear recovery evidence. In the field, key sensors like magnetic flow meters and refrigerant pressure sensors capture vital data, such as chilled water supply and return temperatures, differential pressure, and outdoor dry bulb conditions. At the local control level, variable speed drives on pumps, valve positions, compressor and fan speeds, along with safety and status indicators, help manage system performance precisely. The central position sensor or building management system coordinates essential functions like lead/lag sequencing, anti-cycle protection, failure and recovery logic, and timestamps for event tracking. For evidence, we rely on 1-minute measurement intervals, sub-second event data, command logs, alarms, and raw data exports to validate operations and restorations. The slide also highlights specific engineering and control points, such as temperature and delta T monitoring on chilled water, flow verification, pump speed resets based on differential pressure trends, and fan control reacting to weather and pressure events. Lastly, power metering tied to equipment state and synchronized data exports ensure comprehensive visibility into system starts, availability, and recovery processes. This detailed data integration supports reliable, efficient, and verifiable chiller system performance. In this slide, we focus on key performance, energy, water, and recovery metrics for air-cooled chiller systems in data center MVAC setups. It's crucial to normalize these metrics to simultaneous load, ambient conditions, and equipment lineup because a single green number doesn't guarantee the plant is healthy or resilient. For example, the chiller's coefficient of performance, or COP, is calculated by dividing the cooling output by the chiller's power input, ensuring comparisons are made under consistent capacity and input conditions. We also consider kW per ton, which is derived from the COP, and it should be both certified and measured for accuracy. Other important metrics include the green mark total site energy, representing the sum of all prescribed MVAC kilowatt usage divided by the refrigeration tons, typically evaluated within a 25 to 100% IT load range. We monitor chilled water delta T, which is the temperature difference between return and supply water, and this needs to correlate properly with flow rates. Available duty tracks the total site cooling capacity minus the load, factoring in maintenance and failure states. Starts per hour measure compressor start cycles, helping identify anti-cycle behaviors and volume issues. Ambient and approach temperatures reveal conditions like recirculation and fouling by comparing condensing saturation temperature to incoming air temperature. Finally, recovery and water usage effectiveness are evaluated by the time to duty and site water used per IT energy consumed, with clear definitions of the time and water boundaries. The process involves 4 steps. First, establishing a baseline using load, ambient, and lineup. Second, normalizing within the same parameters and intervals. Third, diagnosing through capacity, flow, pressure, and power analysis. And finally, closing the loop by correcting issues, retesting, and restoring system performance. One key advantage highlighted here is that air-cooled systems eliminate the need for routine cooling tower water. But every site water use must still be reported within approved water usage effectiveness boundaries, along with recovery milestones backed by synchronized data. This comprehensive approach ensures we maintain reliable, efficient, and sustainable MVAC operation. Here we're focusing on the critical concept that redundancy is a tested state, not just a nameplate count. This means it's not enough to simply have backup equipment on paper. The system must be actively verified to ensure it can handle faults. When a lead fault occurs, the system isolates the water and power or control boundaries to contain the issue. While the duty unit is running, it maintains minimum flow and stable chilled water supply, which is essential for steady operation. Before starting a standby unit, the system proves there is adequate flow to protect the compressor. The fault handling process follows 5 key steps. First, detecting the fault and any capacity deficit. Second, isolating the affected module. Third, starting the standby pump or chiller. Fourth, restoring the required duty. And finally, verifying that chilled water supply and rack inlet temperatures are stable. This sequence ensures continuous, reliable operation in air-cooled chiller systems. This slide covers the commissioning levels for air-cooled chiller systems in data center MVAC applications. We start with commissioning level 1, which focuses on design, submittal, and factory acceptance testing. Here, we establish testable prerequisites such as the owner's project requirements, certified performance maps, and control curves to ensure everything meets the specified standards before installation. Moving to level 2, the emphasis shifts to installation verification, including checking equipment tags, access clearances, sensor locations, and ensuring proper isolation and drain setups. This step is critical to confirm the system is correctly and safely installed. Finally, level 3 involves startup and site acceptance testing, where the system undergoes cleaning, safety checks, point-to-point verification, flow testing, and tuning of sequences and alarms. Once these stages are successfully completed and all blockers are closed, the system is authorized to proceed to the next commissioning phases. These thorough checks ensure the chiller system performs efficiently and reliably from design through startup. On this slide, we focus on moving from component-level proof to demonstrating whole system resilience with time-aligned evidence. The key process is the heat load test, which involves several steps such as factory performance review, evaporator flow proof, chiller start and stop tests, fan bank staging, and the loss of one chiller test. This ensures the functional performance of the air-cooled chiller system. We also conduct integrated scenario tests to provide restoration proof. Here, we apply a representative load, reconcile it with the measured duty, hold conditions until stable, and carefully record any uncertainty. In functional performance testing, we initiate one controlled failure to verify both automatic and operator responses, while checking residual capacity and temperature excursions. Restoration proof includes returning the system one controlled step at a time, confirming standby availability, closing overrides and alarms, and signing off on restoration. This comprehensive approach ensures that the system not only performs under ideal conditions, but also demonstrates resilience and effective recovery under various scenarios. Finally, keep in mind, this training example requires declaring all assumptions, with final selections needing approval based on project and vendor data. This thorough methodology is critical for reliable and efficient data center MVAC system operation. In this module, we focus on the final acceptance criteria and the evidence pack necessary for air-cooled chiller systems in data centers. Before testing begins, it's crucial that we agree on pass or fail rules, ensuring each rule has a clear test method, synchronized evidence, an authorized witness, and a closeout owner. Key acceptance criteria include operating the chiller at site ambient conditions with the required load plus an approved margin, performing representative high-ambient load tests, and verifying thermal continuity within approved rack inlet envelopes. We must also ensure minimum evaporator flow never drops below OEM limits, monitor start/stop valve transitions with proper flow and alarm records, and test rapid recovery times from start to full duty. Restoration involves confirming normal lineup, clearing alarms, and performing a controlled return with a functional retest, all supported by signed restoration documentation and indexed evidence. These steps, ready, execute, prove, and restore, form the backbone of a thorough and reliable acceptance process. This slide covers the integrated test for utility loss and full cooling recovery in air-cooled chiller systems, a critical procedure in data center MVAC operations. We start by using a representative load with synchronized clocks and calibrated instruments, ensuring we have explicit abort limits in place for safety. Preconditions include having a protected load, sufficient thermal margin, proper buffer or thermal energy storage levels, a normal and standby lineup, adequate generator capacity, and rollback authority if needed. The execution timeline tracks key milestones such as the initial source loss, usable bus confirmation, chilled water flow, compressor startup, reaching 80% duty, full duty, and a stable hold period. Passing the test means meeting declared milestones and staying within the thermal envelope, while aborting occurs if safety concerns arise, OEM limits are exceeded, or we see uncontrolled pressure, flow, or rack inlet issues. Finally, evidence is gathered through raw data trends, sequence of events, video recordings, duty calculations, alarms or overrides, defect ownership, and retesting both normal and standby modes. This thorough approach ensures reliable full cooling recovery under utility loss conditions. On this slide, we focus on the failure mode register for air-cooled chiller systems in data center MVAC applications. The key process here is to detect issues, respond automatically, and then restore normal operation. We start by ranking the consequence and common mode exposure of failures, ensuring that automatic responses are effective and that residual duty is maintained. For example, if there's condenser-air recirculation causing high pressure or loss of capacity, the system increases fan speed, derates the unit, or starts an available module to compensate. Operators then remove the cause and verify that the site duty and pressure are back to normal. Similarly, issues like controller reboots, voltage faults, or low evaporator flow have predefined automatic responses such as starting alternate modules or inhibiting compressors while approved recovery steps are proven. Importantly, at the common mode hold point, The system does not declare resilient cooling until all shared resources like headers, power, controllers, remote sensing, and airflow dependencies are thoroughly reviewed and tested. This ensures a robust, tested recovery path before proceeding. This slide outlines the troubleshooting workflow for air-cooled chiller systems in Data Center MVAC setups. The first and most critical step is to stabilize the thermal service/emphasis, ensuring IT operations are protected by starting approved alternate paths and suspending non-essential work. Next, we verify the system's state by checking modes, permissives, and actual equipment lineups against commands. Then, it's essential to validate sensing through local gauge cross-checks, calibration, and timestamp alignment to ensure accurate data. After that, we isolate the domain by investigating airflow, water, refrigerant, power, control, and network factors to identify any common mode causes. When moving to correct the issue, only authorized repairs or settings changes should be made, with a single controlled change recorded both before and after. Finally, recovery must be proven by holding representative loads, confirming alarms and standbys are functional, and restoring and signing off on evidence. Remember, at any point, we must hold if safety, residual capacity, isolation, sensing validity, authorization, or restoration proof is uncertain. The entire process forms an evidence chain from the initial condition through to the updated baseline, ensuring thorough and accountable troubleshooting. This slide outlines the standard operating procedure for air-cooled chiller systems, focusing on start, stage, recover, and restore phases. First, we must operate strictly under declared authority and ensure the entire water and electrical path is proven before refrigeration begins, while always preserving the OEM anti-cycle limits. The process starts with the ready phase, where we check lineup, chilled water level and valves, and confirm controller and power health. Then, in the prove flow phase, we start the duty pump and confirm the flow path is open with independent flow above the OEM minimum. Next comes the enable phase, ensuring the chiller is ready, the compressor starts, and the fan and pressure controls are active. During stage, we monitor load, chilled water supply trends, site duty, starts, and generator step load to keep everything within limits. The monitor phase involves observing ambient conditions, temperature sensor errors, capacity margin, and rack inlet envelope to maintain optimal performance. Finally, in the stop/restore phase, we unload the system, allow pump overrun, and confirm normal lineup and standby readiness. Additionally, the fault path emphasizes detecting faults, preserving local safety, starting alternate chilled water or chiller paths, bridging with thermal volume, verifying measured duty and thermal envelope, and restoring normal and standby readiness. Crucially, there are strict prohibitions against starting without proven flow, rapid recycling that ignores OEM minimum off times, forced overrides outside approved authority, and closing out before readiness is proven. This approach ensures reliable and safe operation at all times. This slide covers essential maintenance practices for air-cooled chiller systems, focusing on preserving capacity and ensuring a rapid restart. Preventive and predictive maintenance are key to keeping these systems running smoothly. Maintenance is only considered complete after proper isolation, measured functional proof, and documented return to normal and standby service. Starting with the condenser-air side, it's crucial to clean and straighten coils, clear the discharge area, inspect fans and variable frequency drives, and monitor trends against site capacity. For refrigerant and compressors, we check for leaks, monitor pressure and temperature, verify safeties, confirm the rapid start option, and observe the witnessed loading curve. Moving to the evaporator and chilled water system, we focus on flow, temperature difference, and pressure drop, maintain strainers, ensure water quality, and manage minimum volume and bypass settings. Pumps and valves require inspection of bearings, seals, and variable speed drives, proof of isolation, assurance of standby auto start, and independent flow proof. Sensors and meters must be calibrated, correctly located, record proper units, timestamp data, and support 1-minute measurement and verification, as well as event capture. Lastly, controls and power systems should have reliable controller ride-through, well-planned generator sequence, coordinated lead and lag operations, alarms, backups, and strict change control. The return to service gate marks the point where work is fully closed, guards and safeties are restored, isolation is removed under authorized control, functional and restart tests are passed, and normal and standby readiness is officially signed off. As we dive into emergency operating response for air-cooled chiller systems, remember that life safety and thermal stabilization come first. It's crucial to preserve evidence and restore systems deliberately to avoid further issues. When there's a loss of normal power, you need to confirm the alternate bus and controller state, verify the chilled water path, monitor the chilled water supply and rack inlet rate of rise, and start the approved rapid recovery sequence. If the chiller fails to restart, start an alternate module or train, preserve the original equipment manufacturer safeties, compare the remaining thermal bridge with the predicted recovery, and escalate the situation early if needed. In conditions of high ambient temperature or airflow constraints, remove any recirculation or obstructions, maximize the available fan or circuit within limits, and only use approved setpoint or load actions under incident authority. Finally, if the thermal bridge is nearing its limit, invoke the approved IT load action, prioritize protected spaces, record the thermal maximum, and restore full duty and standby operations before closing out the response. In this practical lab, we're focusing on high-ambient N+1 selection for air-cooled chiller systems in Data Center MVAC setups. The key objective is to select the right number of modules based on the site conditions and verify that the system can maintain the required capacity, even if one module goes offline. To do this, we start by inputting critical parameters like the protected load, design margin, site ambient temperature, chilled water temperatures, and certified module data. Using these inputs, we determine how many duty modules are needed, the N+1 count, system flow, and the residual capacity margin. Our method involves derating the system at actual ambient and altitude, factoring in allowances for recirculation and fouling, calculating the design duty, and then applying the N+1 redundancy after sizing the system. This ensures our selections are robust under real-world conditions. The outputs from this process include a detailed calculation sheet, a marked-up OEM selection, a module staging plan, and power and airflow checks. Our pass criteria require that the system meets the necessary duty levels in normal, maintenance, and failure states, maintains minimum flow and volume, and complies with electrical and clearance standards. Understanding these steps is crucial to ensuring a reliable and efficient air-cooled chiller operation in demanding data center environments. On this slide, we're focusing on Module 03, which covers air-cooled chiller systems, as part of our advanced training for Data Center MVAC. The practical lab involves building a green mark TSE budget. The key task here is to allocate the platinum cooling power cap across the entire prescribed ACMV boundary. Our objective is to demonstrate a training case that achieves less than or equal to 0.68 kilowatts per ton of refrigeration, while maintaining the necessary capacity and redundancy. Moving on to calculations, remember that cooling in RT is derived by dividing the kilowatts by 3.517. The power cap is calculated as RT times 0.68, and TSE is the total prescribed ACMV kilowatts divided by measured RT. For controls and optimization, we test at various load levels, 25, 50, 75, and 100%, and adjust chilled water temperature, fan and pump speeds, and module staging accordingly, always ensuring we never conceal any unavailable capacity. Finally, in field proof, we monitor 1-minute intervals for power, flow, and temperature under stable load and ambient conditions, perform uncertainty and boundary checks, and verify worst point acceptance. This thorough approach ensures accurate and optimized chiller performance for data center cooling. Now, we're focusing on Practical Lab 3, where we simulate and prove blackout recovery for an air-cooled chiller system. The goal is to write and evaluate a complete utility loss test, tracking everything from the initial power outage to restoring normal operation and standby readiness. The scenario starts by removing the normal utility power while operating at a representative load. Throughout this, we rely on alternate power sources, buffer thermal energy storage, and standby equipment to keep the system stable. It's critical that full duty and normal readiness are restored before we conclude. Our response involves several key steps. First, detecting the loss of utility and transferring to backup, then proving the chilled water path is intact, followed by restarting the compressor, achieving at least 80% duty, progressing to full duty, and maintaining the thermal envelope to protect the load. We always consider residual risks, including potential compressor restart failure, generator step loading issues, buffer depletion, common controls or timestamp errors, and challenges posed by high ambient temperatures. For evidence, we gather raw sequence of events and trends, perform duty calculations, monitor maximum rack inlet temperatures, maintain a milestone table, document any defects, and ensure all restoration steps are signed off. Remember, terms like CHW refer to chilled water. COP is coefficient of performance. VSD stands for variable speed drive, and CPOS means chiller plant optimizing system. This structured approach ensures we can confidently recover from a blackout while safeguarding the data center environment. On this slide, we focus on the critical concept of handover evidence and operating readiness for air-cooled chiller systems in data centers. The plant is only considered ready when technical, procedural, and competency evidence are all complete. Starting with design, key elements include the owner's project requirements, basis of design and standards matrix, as well as calculations for high ambient conditions, redundancy like N+1, and certifications such as LEED and Green Mark. Moving to installation, we must verify as-built documentation, proper tagging, adequate access and clearances, thorough cleaning and pressure testing, electrical and control dependencies, and meter calibration. For controls, important factors are the point schedule, operational sequences and timing, rapid restart options, alarm and backup systems, and strict access and change management. Testing must be accepted and documented. Finally, operational readiness hinges on having current standard operating and emergency operating procedures and ensuring only authorized personnel with the right competencies are involved. Understanding these layers ensures the chiller system performs reliably and efficiently from day one. This slide outlines the competency assessment for Module 03 on air-cooled chiller systems. Here, learners are expected to demonstrate engineering judgment through calculations, sequences, and providing defensible evidence. They need to explain several key concepts, including the complete heat path and failure domains, the logic behind LEED and Green Mark certifications, and how uptime and TIA outcomes relate to owner timing. In addition, learners must calculate critical parameters like site duty and flow, annual cooling energy, and the impact of high ambient conditions on N+1 redundancy, along with the thermal buffer. Diagnosing issues is another vital skill, focusing on problems such as condenser recirculation, fouled coils, low chilled water delta T, delayed restarts, and dependencies on generators or controls. The assessment also involves operating the system correctly, proving performance metrics, and escalating issues as necessary. We emphasize understanding the system across normal operations, failure states, and restored readiness. Key terms like CHW for chilled water, COP for coefficient of performance, VSD for variable speed drive, and CPOS for chiller plant optimizing system are fundamental to grasp throughout this module. On this slide, we focus on the essential standards and references needed for designing and operating data center MVAC systems. It's crucial to always use current license standards, approved project records, and certified vendor data to ensure accuracy and compliance. When considering availability and topology, we rely on guidelines like the Uptime Institute Tier Standard and the ANSI/TIA 942C rating model, which define infrastructure reliability. For sustainability and performance, certifications such as LEED and the BCA-IMDA Green Mark provide clear pathways and thresholds. Thermal and equipment standards include the latest ASHRAE standards, AHRI certifications, and OEM data to guide proper system functionality. Remember, certified data, witnessed proof, and decisions from certifying authorities and licensed consultants take precedence over training summaries. Keeping thorough project records, including operational requirements, calculations, and test results, is essential for long-term asset management. Finally, always verify system performance under real-world conditions, ensuring readiness and reliability. In this final synthesis of air-cooled chiller systems, let's focus on building a resilient plant. This means a system that maintains its capacity, efficiency, and recovery time not just under normal operation, but also during maintenance and even failure scenarios. Starting with the design basis, it's crucial to select equipment based on the actual site ambient conditions, ensuring you clearly differentiate between design margin and redundancy. Also, protecting minimum flow, system volume, and equipment limits plays a big role in system resilience. Moving to performance commitments, supporting your chosen LEED or green mark path is essential, along with meeting targets for TSE, PUE, WUE, and refrigerant strategy. Defining timed recovery milestones helps track your system's ability to bounce back after disruptions. Finally, operating proof ties it all together. You need synchronized electrical, mechanical, and thermal data, along with representative failure and recovery tests. This must be coupled with signed restoration records and having competent operators ready to manage the system effectively. Remember, understanding these aspects along with key terms like CHW, COP, VSD, and CPOS ensures your chiller system is optimized and sustainable.